In this section, we're going to be talking about exponential functions. Now, these functions are going to be dealing with a lot of exponents. I think they're super fun, super neat, and for the most part, pretty easy. Now, you just have to make sure you know your powers, and if you look at the notes that I gave you, you have that nice power sheet listed there at the top half. So I gave you one in class, it's also there in the notes, so make sure that you have that on hand for all of the problems that we're going to be doing, so it's really easy to find the powers and the answers that go along with that. So exponential functions. Here's what we know. An exponential function is of the form f of x is equal to a to the x, where a, the base, is positive and that base does not equal 1. So this is how we describe an exponential function. Instead of having x as the base and dealing with things like x to the second or x to the third power, our power now is what varies. So you have some kind of base, and you're going to have a power that's going to be changing. Now, for a lot of the graphs that we do, we're going to see that here in just a moment, I deal with a base of 2 because it's a lot easier for us to plot points and really get an idea about the shape. Now, you might see different bases in the homework or in other real-world examples, but I'm just trying to give you an idea about what the graph looks like so that you can, graph using the same transformations that we've been using this whole semester. Okay, so when it comes to exponential functions, there are a couple of things that we need to know about this. Number one is that a to the x is a unique number for every real number x that you plug into it. Okay, so that means no matter what value you plug in, it's going to be unique. So if whatever the base is, if I raise it to the second power, the answer that I get, well, the only way to get to that answer is by having a power of 2. And what this does is that leads to this idea that f of x equal to a to the x, this exponential function, is a one-to-one function. Now, keep in mind that if things are one-to-one, that means they have an inverse. And the inverse of the exponential is something we're going to be talking about in a couple of sections. And these guys are very closely tied together. That's why they're inverses. Here's the other thing we get from this, based off of this being a one-to-one function, is that if you have a to the x is equal to a to the y, well, this is only going to happen if those powers are the same. Now, the double arrow here means if and only if. So it means if you have this, then you can go here. It also means if you have this, you can come back over here. So to emphasize this, I want to point out here that these guys have the same base. So if you have an equation and the two bases are the same, that means you can then take those powers and set them equal. That's part of the whole thing about that exponential function being one-to-one. Okay? Now, since we have that, what I want to do is I want to look at a couple of small little exponential equations before we get to the big section of those guys next. And just run through that so you can see what I'm talking about here with this second statement. So we're going to run into equations, and this is really just scratching the surface of the kinds that we're going to see. If I do 5 to the x is equal to 125. This last statement up here says that if the two sides of your equation have the same base, then you can take their powers and set them equal. Well, right now these guys don't have the same base, unless I do some rewriting. Because on the right side of the equation, I can rewrite 125 as 5 to the third power. And now, since these guys have the same base, according to the statement that we have right here, if these guys have the same base, that means that their powers must be equal. So x must equal 3. And so there you go. And this is something we're going to see a lot of times. Earlier on this semester, we saw x in weird, unusual places. We saw x inside absolute values, and we saw how to get rid of the absolute values and get our two equations. We saw x inside of a radical, and we talked about how we use the power property so we can get rid of the radical and then have a normal-looking equation to solve. We saw x in the denominator, so we would clear out the fractions and solve the resulting equation. Now, we are seeing x as a power, and we're going to talk about how do we work with that? How do we get it to be not in a power, but into another equation that makes more sense, something that we can solve? So here, as long as you can write these guys with the same base, it's not going to be too bad. Now, one of the last things that we will see towards the end of the semester will be, what if these bases can't be the same? What if this has a base of 5 and this one has a base of 3? How do we work that? Well, that's going to be a job for the inverse of exponentials. But don't get too excited. We'll get back to that guy here sooner than you realize. All right, so let's do another example. If I take 4 to the x equal to 8 to the x plus 5. What we're trying to do here is to rewrite each side of the equation so that they have the same base. Now you look at that power chart that we have at the top of this document, you're going to see that 4 and 8 are based off of the same number, that being 2. So 2 is the common base. And so what we do is that we rewrite each of these guys using that common base of 2. So if you look above, you know that 4 can be rewritten as 2 squared, and 8 can be rewritten as 2 to the third. So this is good for us, so we can identify they have a common base. Now, we do need to remember how to work with exponents, and we need to remember that when you have a power raised to a power, we multiply. So that's going to be 2. When you multiply these guys right here, okay, so that's going to give me to the 2x equals 2, and over here, power to a power yet again. So you're going to be multiplying those guys. So you have to distribute. That's going to be 3x, and then 3 times 5 is 15. And just as we saw in the last example over here, we now have an equation where you have the same base. And as we saw, if we have the same base, that means that those powers must also be equal. So that means we can say that 2x is equal to 3x plus 15. Notice that we don't really do anything with these bases. They're just here to show that each side of the equation has the same base. And as long as they have the same base, you just take these powers right here and you form the equation from that. And now you have a nice linear equation to solve. Okay, a couple of ways of doing this. So let's just go ahead and subtract 3x, because we've got the 15, that's the only constant term that we have, so just leave that on the right side. Negative x equals 15, and then divide by negative 1, and you get x equals negative 15. And what you're going to see as we dive into more of these exponential equations, the process is all the same. We're just going to have to remember some of those techniques for dealing with exponents that we saw a long time ago. And we have to make some slight little manipulations. But before you know it, you'll have the same base, like we have right here. And you take those powers, you set them equal, and you solve. But up next, we want to talk about what do the graphs look like for exponential functions. So stick around.